This is Lab 1 Constant Velocity by Aaron Christian. The purpose of this lab was to figure out that if an object had zero net force acting upon it, would its movement be in a constant velocity? We found this to be true, and by finding this to be true, we proved that the kinematics equation for velocity and position can be also true. At the top of this slide, we have the velocity equation. This is what we're looking for to find if there is a change in velocity in what we're trying to prove through this experiment. Below, we have two graphs, a green and an orange graph. The green graph shows the velocity versus time, while the orange graph shows the distance versus time. So in the green graph, we see that it is horizontal, which shows that there is no change in velocity throughout the time interval that we tested. And then on the orange graph, we have a linear line that heads up, which means we're moving in a positive direction and we're moving at a constant velocity throughout that time interval. On the right, we have our source video. So, yep, go. The part of that video that we really were looking at was the beginning part where it went across the meter stick shown below. The system that we're measuring in this video is the car that ran across the track, and then the surroundings include everything besides the
Go.
car. One of the initial conditions was that we kind of chose to ignore air resistance and friction acting on the car. At least as far as with air resistance and friction, their impacts were basically not big enough to be able to measure in this experiment. This slide is our GlowScript code and our simulation. So in this video, which I'm playing right now, the blue ball, is acting as our car, while the yellow line is the distance that we covered with the car, with the yellow ball being the original starting point. That ball is moving the same speed that our car moved, which is about a meter per second. And in our code, we really just plugged in values. And so most important values were what is our net force that we should expect to be acting upon the ball. And so we expected there to be a zero net force acting upon the ball. And then we have the ball's velocity, which came out to be like a meter per second, and the ball's mass, which was 0.87 kilograms. Our sources for error could be how we use the software tracker. So for tracker, you have to identify each center point at each frame. And so something as simple as placing it a little bit below or a little bit behind can't affect our data points, but the result is basically the same even with the human error. For our what if slide, we have two questions. What if the car were to slow down? So if the car were to slow down, the first thing we would most likely do is look on the track and see if there's anything that could have caused increased friction, anything that could have caused a force upon the car. So if there was a magnet on the track, if there was maybe increase in airspeed around the car that could have slowed it down, or if there's like something sticky on the track that could have slowed down the tires. Our next question is, what does it mean if the car were to speed up during the test? If the car were to speed up, one of the only things there was two possible scenarios. So either gravity, so our track could have been slightly pointed down, and so which gravity would have had an acting force to pull it down with, or maybe there was air pushing the car from behind, causing it to pick up speed. In conclusion, with this experiment, we found Newton's second law to be true, and we also found that computers are able to simulate what we experience with Newton's second law.